Welcome, everyone, and thank you for attending today's SEL webinar, Simplifying Nerc PRC 027 Compliance. My name is Jeff Owen. I am a Senior Marketing Program Manager from Schweitzer Engineering. I will be today's moderator. I would like to mention a few housekeeping notes before we get started. This is an audio-only broadcast. All participants are muted. Today's webinar will be a one-hour session, including questions at the end of the presentation. This webinar will be recorded and will be made available within 72 hours after today's event. If you have any questions throughout the presentation, please submit them to all panelists with the Q&A tool at the bottom right-hand corner of the application. Any questions that are not addressed during the live event today will be answered by our experts via email. Please also note that we will be offering PDH credits for participation in today's live event. To receive these credits, you must attend at least 75% of the webinar. No partial credits will be awarded. You will receive your certificate via email. Our presenters today will be Brent Hemrich, Group Manager, SEL Engineering Services, Sneha Basaduvan, Protection Project Engineer, SEL Engineering Services, and Rajesh Arumugam, Engineering Services Manager. With that, I will now pass the microphone over to Rajesh, and we can get started.
Hello, everybody. Welcome to another great presentation from SEL. At the end of this presentation, you should have a good understanding of the Nerc PRC 27 standard, some pain points that the industry faces, and SEL's approach to helping our clients achieve compliance. On behalf of SEL, allow me to extend a warm welcome to you today. Let me provide you with some background on SEL Engineering Services. SEL Engineering Services brings industry-experienced engineers for the best possible solution in great quality and great customer service that we all have come to expect from SEL. Over 600 engineers, designers, field personnel, and support staff are focused on providing expertise to our customers worldwide. The geographic diversity in organization provide the flexibility to draw on skills, knowledge, and expertise from across engineering services and the larger SEL organization in general. SEL Engineering Services fills a growing need in the electric power industry as companies deal with the impacts of smaller engineering staffs, increasingly complex requirements and needs. We started by primarily selling to electric utilities, but as our product portfolio grew, so did the number of industries we partnered with. SEL now designs and manufactures reliable solutions for a variety of industries, including pulp and paper, transportation, water and wastewater, education, healthcare, government, mission-critical facilities, and oil and gas and petrochemical operations. All utilities, G&T cooperatives, and independent power producers face challenges ranging from how to integrate renewable energy sources into the power grid to how to provide perfectly reliable power in hospitals and research facilities. We like to say that SEL products are the brains behind many of the systems that address these challenges in a way that is both cost-effective and improves worker safety. Here's an introduction to our speakers today. Myself, I have a utility and a regulatory background. I spend time following various FERC orders that affect the industry. Been with SEL for 12 years, and I currently lead a team of automation, protection, and field engineers that provide value-rich services to our clients. Sneha has been with us a little over 9 years, has authored many technical papers, notably one that talks about the risk of misoperations in transmission protection. She has designed Nerc PRC 27 solutions for several customers, and her background in utility protection philosophies and standards makes her a great choice for speaking today. She'll be speaking on the actual PRC 27 standard and some intricacies involved being compliant to the standard. Brent is a group manager in our protection services group, leading a team of talented engineers and designers. Been with SEL for 11 years, is well versed with utility practices, especially in transmission line protection, including many years of commissioning substations and power plants. Brent will be talking about how SEL can help utilities be compliant to PRC 27. SEL has been providing Nerc PRC compliance services for nearly a decade. We have a track record of knowing compliance and regulatory landscapes, participating in technical conferences, standards committees, etc., helps us keep a close watch on those industry best practices. Teams stay connected as Nerc standards get discussed and rolled out, and that helps our teams stay ahead of the curve. As a matter of fact, our setting calculations are Nerc compliant, Nerc PRC compliant by default. In fact, Nercs just become a part of our life at SEL. So what do we offer? The utility, the G&T cooperative industry, and the independent power producing entities have found great benefits working with us. As we discussed, our extensive experience with Nerc PRC compliance sets us apart. Our PRC 27 services are customized and adapt themselves very well for your existing processes. Our audit documentation and deliverables are meaningful, basically audit ready. We utilize an internal software tool for PRC 27, and we can discuss more on later slides, that helps with very high quality outputs, very short lead times to provide those deliverables at competitive prices. Here's a quick introduction to Nerc. Nerc was founded by the electric utility industry to develop and promote rules and protocols for the reliable operation of North America's bulk power system. Nerc oversees reliability and security for quite a large interconnected electricity system that provides electricity to approximately 370 million people, has nearly 18,000 generating units and thousands of miles of transmission lines. Some of Nerc's roles include working in the industry to develop those reliability standards, monitoring and enforcing compliance using those reliability standards, and assessing monetary and non-monetary penalties for non-compliance, evaluating the performance and future reliability of the bulk power system through a comprehensive set of annual assessments. As you can see on this map, Nerc is also split into several reliability organizations in Canada and the United States. So on June 7th, 2018, FERC issued an order, order number 847, the final rule for coordination of protection systems during faults and specific training for people involved. The final rule approved reliability standards PRC 27-1, which relates to the coordination of protection systems for performance during faults, and PER 006-1 that relates to the training for personnel. Were also included the retirement of currently effective reliability standard PRC 001. In the docket, Nerc indicated that reliability standard PRC 27-1 would provide a clear set of requirements that obligate entities to implement a process for establishing and coordinating new or revised protection system settings, and periodically study protection settings that could be affected by any incremental changes in the fault current to ensure that these protection systems continue to operate in their intended or desired sequence. Sneha will now talk more on the actual PRC 27 standard, some of those intricacies involved, some of our experiences with it, and about how SEL Engineering Services can help you overcome some of the difficulties and provide the solutions for PRC 27. On to you, Sneha.
Thanks, Rajesh. So let's take a detailed look at what the PRC 027 standard really is, its purpose, and the requirements as mandated by Nerc. The PRC 027 is applicable to transmission and generator owners and distribution providers who own protection systems installed to detect and isolate faults on the BES elements. So what really is Nerc PRC 027? This is a reliability standard that aims to maintain coordination of protection systems that are installed to detect and isolate faults on the bulk electric system. And here, by coordination, I mean that these protection systems should operate in an intended sequence during a fault condition. So to achieve coordination, this standard mandates entities to establish and follow processes necessary to mitigate the risk of misoperation and improve grid reliability. I think it also outlines 3 requirements to help achieve this. The first one, requirement R1, requires applicable entities to establish, develop, and document standard processes and philosophies to ensure that protection systems operate in the intended sequence during fault conditions. These process documents shall include the update and review processes of short circuit model data and development of protection settings. In addition to this, it shall also include how coordination will be carried out when the applicable BES elements are electrically connected to a separate functional entity. In the standard, Nerc neither mentions any specific coordination time interval nor contingencies to be considered for the coordination study. We therefore recommend that entities develop and document a criteria for performing these coordination studies based on the industry standards and entities' best engineering practices and existing philosophies. Really, to achieve consistency in relay settings developments, right, and coordination across the entity and their interconnects, we recommend that the criteria for coordination be defined and documented as part of the established processes and relay philosophies developed as part of this requirement. To really summarize what the intent of the R1 is, it is to establish a solid foundation with the help of processes to minimize the possibility of errors and basically ensure consistency while developing settings, maintaining the short circuit model, and communicating with your interconnect facilities to achieve coordination and improve grid reliability. A short circuit study is nothing but an analysis of an electrical network that determines the magnitude of currents flowing in the network during an electrical fault. As we can guess, the results of a short circuit study are really only as accurate as the information that its calculations are based on. Therefore, we believe that a review of a short circuit model prior to performing coordination study is a very important step in this compliance. What do we mean by short circuit model verification? This review should actually include verifying and confirming that the network model used for the short circuit study accurately represents the configuration of the actual system. Another thing that comes to my mind when we speak about verification is to include verification of lines, transformers, and generator impedances, as well as mutual coupling data to be reviewed against the data provided by planning and operations, manufacturer nameplate information, and any data provided by interconnecting facilities. Over time, incremental changes in fault current can accumulate enough to impact the coordination of a protection system function. Therefore, to mitigate this risk, requirement R2 was introduced and requires entities to periodically perform coordination studies, review and update fault currents to mitigate the risk. The standard provides 3 further options under R2. Option 1 can be called as a time-based methodology. So entities really selecting this option would need to perform a coordination study in a time interval not to exceed 6 calendar years. So let's say that the entity performs a wide area coordination study in April of 2022. The next time they'll need to perform a coordination study should be no later than 6 years from April 2022. The advantage of this option really is that I think it eliminates the necessity of establishing a fault current baseline and periodically performing those fault current comparisons. It also provides the flexibility to choose the interval of up to 6 calendar years for performing this coordination study. The second option is a fault current-based methodology. So entities selecting this option would periodically check for a 15% or greater deviation in fault currents against an initial fault current baseline established. Now, this fault current baseline is typically established by placing a 3LG and a 1LG fault on each bus to which the BES element is connected to. Note that the 15% deviation is the maximum fault current deviation that was established based on generally accepted margins for which incremental fault current changes would not really interfere with the coordination study. So this maximum value really provides the entity with sufficient flexibility to choose a fault current threshold that best caters to their protection philosophy and standard practices. To make it more clear, let's take an example. So let's say if an entity wanted to be more conservative, they could go with a lower percentage deviation, for example, 5%, or even for that matter, 10%, just so long as that percentage deviation is not greater than 15%. Also, it's important to note that if the entity selects this option 2, the initial fault current baseline needs to be established prior to April 2021, when this standard takes effect. Now, if an initial baseline was not established by the effective date of this reliability standard, let's say because of a previous use of an alternate option or an installation of a new BES element, the entity may establish the baseline upon performing a protection system coordination study. Option 3 really is a combination of the above two, which is a combination of the time-based methodology and a fault current-based methodology. Now, do note that the 6 calendar year time interval was really selected as a balance between the manpower required to perform the studies and the potential reliability impacts created by incremental changes of fault current over time. To decrease the possibility of introducing errors and reducing the risk of a miscoordination, a consistent and sustainable approach to updating and developing relay settings is key. Therefore, requirement R3 was introduced and expects that entities follow the processes that they establish as part of requirement R1 to help achieve the objective of R3 and the very intent of this standard. That's why it's really important that the processes set in place as part of requirement R1 be robust, sustainable, follow, yet flexible to cater to the ever-changing needs of the entities. These processes really form the very foundation of the standard and is the most important step in achieving compliance. Now let's see what are the applicable elements in this standard. The protection system functions applicable to this standard are listed on this slide. The reason these elements were really chosen is because these elements utilize AC currents in their measurements to initiate tripping of the circuit breaker. Now, because of this very feature, coordination of these elements are susceptible to changes in magnitude of available fault current at any given time. So to summarize, these elements were included in the standard for two main reasons. The first is because they are set based on available fault current levels, and two, which is more importantly, that their functions require coordination with other protection systems. Distance elements are applicable to this standard only when in-feed is used to determine its reach. When in-feed is not used in calculating the distance element's reach, it is not susceptible to changes in magnitude of available short circuit fault current, and therefore really would not be applicable to this standard. Another thing would be the effect of mutual coupling. Now we know that mutual coupling really depends on the changes in magnitude of fault current. So if the distance element were developed to include the effects of mutual coupling, then they would be applicable to this standard. So to understand the effects of system changes on relay settings and coordination, let's consider a simple example. For the purposes of this discussion, we're going to assume that all of the breakers highlighted in red symbolized a closed breaker, and breakers highlighted in green symbolize an open breaker. So as you can see in the slide, line 1 and 2 between station B and C consists of a tab bus as shown. So let's say a fault occurs in the locations shown on this slide. Now, assuming that all relays are really set correctly and properly coordinated, we would really expect that relays associated with CB1 and CB2 detect and isolate the fault first. Relaying associated with CB3 will really provide a time delay backup in the event CB1 fails to operate. Now, what if the tab bus was upgraded to a station bus D as shown? This upgrade would not only affect the system layout, but would also result in associated changes with fault current magnitude, right? So how does this affect the settings? So the relay settings associated with CB1 and CB2 would need to be recalculated per the updated system configuration. Additionally, new settings would need to be developed on relays associated with CB5 and CB6. Also, relays associated with CB3 and CB4 may need to be revisited to ensure coordination in the updated system configuration. So let's consider a fault in the same location discussed previously. If the existing relay settings were revised to accommodate the system changes and achieve coordination, the intended sequence of operation would really be as follows. First, relays associated with CB1 and CB5, not CB2, would need to detect and isolate the fault first. Then, relaying associated with CB3 and CB2 would provide time-delayed backup. And this would be in the event that, let's say, CB1 or CB5 fail to operate. However, what you can see on the next slide is not the intended sequence of operation, correct? Because remember, we said that the breakers that were closed were highlighted in red, and the ones that are open are really highlighted in green. So for this fault, really relays associated with CB1, CB5, CB2, and CB3 operated to isolate and to detect and isolate that fault. Why did that happen? Could it be that we forgot to update the relay settings associated with CB2 for the new line parameters and system layout? And probably given that we even missed this, could we safely assume that relaying associated with CB2 was never really coordinated with the new relaying at CB5 to achieve the intended sequence of operation for this fault? Also, why did relaying at CB3 trip when CB1 tripped for the fault? These are some things to consider when establishing processes, relay philosophies, and conducting peer review checklists and reviews to eliminate loopholes and minimize human error. Now that we've understood what the PRC027 really is about, let's briefly discuss the main difficulties faced by entities to comply with each requirement of this standard. Often, entities lack company-wide protection philosophy standards and documents to help manage their system-wide coordination. Processes may not internally mandate protection engineers to perform consistent coordination studies, or there may be multiple versions of a short circuit model and no procedure to retrieve the most recent model. Or it could be that models may be incomplete or inaccurate. As discussed previously, all of these increase the risk of protection systems to not operate in an intended sequence as expected, and therefore need to be addressed. This is the very reason that Nerc developed this standard with the intent of reducing human error and risk of incorrect model and setting. Maintaining a well-designed and documented process, creating philosophy documents, and standard setting calculations can serve as a solid foundation to assisting protection engineers in maintaining a coordinated system with consistent processes at all times. For requirement R2, we understand that it's sometimes difficult to coordinate across system boundaries when sharing the electrical connection with another functional entity. Data management of relay settings and documentation of equipment rating and really organizing them in a useful manner for future reference is sometimes difficult to achieve given how many changes occur in a utility system. Additionally, without proper documentation and training, it really is difficult to define a criteria for coordination. And this results in inconsistent expectations for relay settings and also the coordination study, right? So as discussed earlier, the results of a coordination study are only as good as the data used to develop the short circuit model, equipment rating, relay calculations, and setting file. We believe that developing a robust process that considers data and asset management, along with robust philosophy documents that establish expectations for achieving coordination, is vital. So when we come to R3, we've really completed the coordination study at this point. And after performing the study, the next step is to implement the recommended changes per the process document developed to comply with requirement R1. Some entities may not have developed or revised settings or coordination study peer-reviewed by a qualified engineer prior to implementation. This affects the quality of settings and coordination. We believe that establishing robust processes that include peer review checks prior to implementation is key. Additional recommendations that we have include creation of quality checklists, use of standard relay setting templates, and good management of relay settings. Now, Brent will discuss how SCLES can help you overcome these difficulties and provide value-rich services for PRC 027. On to you, Brent.
Thank you, Sneha. Here's SCL's approach to PRC 27. When a utility or a generating facility has a need for PRC 27 compliance services, they almost always have questions on what the standard is all about and what it takes to be compliant. They're usually in different stages of the process depending on their existing work culture, practices, and procedures. Utilities can often have varying interpretations of the Nerc standard, and our services help understand their existing systems, provide simple frameworks, create standardized philosophies, and relay setting templates, and establish robust and easy to follow processes and practices that help future coordination studies be less painful, because after all, the coordination studies do need to be performed every 6 years. SCL understands these requirements and helps our customers comply with the requirement not only in the short term, but also reduce pain points in the long term. So what happens next? Well, we work with the customer to mitigate their pain points and help achieve a compliance to PRC 27 standard. The utility or the generating facility is served with audit-ready reports that they can use immediately. The last box is where SCL performs wide area coordination studies, performs revised relay calculations, updates settings, and implements updates and upgrades. Essentially, we provide a solid, customized, ready to start to finish solution for PRC 27. Our PRC 27 solutions are customized to meet customers' needs. Customers can pick and choose services that help them be compliant. Of course, there's always an option to provide end-to-end services from start to finish. Many of us have established processes in place that ensure compliance to the standard. Many of us find it challenging to keep short-circuit models up to date because systems changes can occur at a very rapid pace. SCL has been building sustainable processes and solutions to help make those updates, ensuring inaccurate models through time. In many cases, we manage the short-circuit models for our customers as well. Another challenge that's very common in our industry is the lack of protection philosophies and consistency in applying these philosophies across the asset footprint. We understand this quite well. We can help you overcome that challenge. Our engineers have developed very many relay settings and application guides, philosophies, reviewed them for utility customers, and we can do that for you as well. The heart of PRC 27 is to create those processes and ensure that there's an area-wide coordination study conducted. Our engineering services organization can perform these studies, provide recommended changes, standardized relay setting calculations, logic, and settings, and carry these through commissioning and energization. On our next slide, we will discuss our SCL internal automated tool that greatly helps us with these tasks, including creating audit reports for PRC 27. So I'm going to talk a little bit about our CDAT tool, which is our compliance and data analysis tool. Fortunately, compliance for Nerc 27 doesn't need to be manual, time-consuming, and an error-prone process. SCL uses internal tools such as CDAT that assist with generating impedances, verification, and discrepancy reports, establishing fault current baselines, and performing wide area coordination studies. The tool eliminates copy and paste tasks, thus reducing errors and increasing the accuracy of the results. It removes error-prone steps from the short-circuit model verification and coordination studies and assists engineers with analysis of results and facilitates compliance readiness. The tool doesn't automate the relay calculation process, since we believe that this is an important step for engineers to apply the art and science of protection and validating the settings. This is important to achieve quality. As you may have guessed, the design of the tool helps us lead the compliance services market. Here's what the tool can do. Automatically generates discrepancy reports to identify errors with settings and port, and validates the settings with respect to Aspen impedances. It runs error-free automated wide area coordination studies in Aspen and helps reduce utility costs by removing manual processes without affecting quality. It generates audit-ready documentation reports for NERC PRC 20, and it does not remove the art and science of protection, as I stated earlier. But it sets the stage for long-term vision for system-wide coordination programs and differentiates heavily compared to manual processes that are error-prone. So how could we help? We sincerely appreciate your time today. As noted on our last slide, we have philosophy documents, procedures for you, as well as automated tools that help us produce high-quality deliverables with increased cost savings. Our solutions are full-fledged from start to finish. SEL Engineering Services is here to help you in NERC compliance audits, particularly PRC 27. Please reach out to us by email, prccompliance@selinc.com, or through our sales channel. Next step will be our Q&A session. On to you, Jeff.
Okay, thank you, Brent. We've now arrived at the Q&A portion of the event. As a reminder, please submit your questions to all panelists with the Q&A tool at the bottom right-hand corner of the application. First up, fault level changes during maximum and minimum plant running exceed 15%. How do you tackle the PRC 27-1 requirement in respect of 15% variation?
So like we mentioned before, this 15% is basically the maximum allowable deviation. And so what we would do is to study your system and go through your existing philosophies and standards to really understand how the system operates and help you come up with that percentage deviation that works well for your system. And like you said, we do have the flexibility to go below that 15%, but not above.
Okay, thank you, Sneha. Another question. In what case element 21 coordination is not applicable or not required as per the standard?
So like I mentioned in the presentation, the 21 element, let's say we set a zone 1 to 80% or a fixed percentage of the line impedance without considering effects of infeed. That would be a case where the 21 element really isn't applicable to the standard because its reach is based on a fixed percentage of the line impedance as opposed to infeed, which will be affected by changes in fault current magnitude. To simplify that, if your 21 element is set based on a fixed percentage of your line impedance and does not account in any way for the infeed seen by that particular element, then the 21 element will not be applicable to the standard. An additional requirement is needed for the ground distance. So let's say you're setting a 21 element on your line that has mutual coupling. Now then that element would need to be set based on the effects of mutual coupling and therefore would be applicable to the standard. Hope that answers that question.
Thank you. Next question. Our utility has some processes, but they're not documented, really don't have any type of philosophy at all. So how could SEL help me?
So if you already have an informal process, maybe it's just not documented, we can meet with your team. We can conduct a round of interviews of sorts and get an understanding of your process and document the process to meet the PRC 27 compliance. If you don't have a process in place for keeping like your short circuit system model up to date, we have customers who have us manage their system models and model updates. So we can take care of the licensing renewal, serve as the point of contact for the model. And we can manage the documentation to meet PRC compliance regarding the model. So please, reach out to us if it's something that we can help you with or you'd like more information.
Thank you. Next question is somewhat related here. Does your team help with the standard philosophy development, setting calculation templates as an example?
Our team works, developing standards, not just for processes and philosophies, but we also work developing standards, philosophies, etc., based on existing utility practices that we may encounter. So the short answer is yes. The long answer is we'll be more than happy to work with our clients to discuss and be of help.
Next up, if I'm a utility that has documentation that is not fully complete or halfway there, how could SEL help us in this situation to be compliant?
I think this kind of piggybacks off of the question that was just presented, maybe a little bit more detailed, but just using like partial documentation you already have, we can help you develop a protection philosophy document that meets PR 727 compliance. So like, for example, if you have an existing calc sheet that were used to set relays on your system, or like a rough document that may have been used in the past that generally discusses your settings philosophy guidelines, this would be, great to help expedite that process. However, the amount of time that would take would largely depend on the number of different types of BES assets owned by the utility. Some customers prefer to cover all BES assets and non-BES assets. Others prefer to only have the document address just BE assets in question. So the depth of the documentation can be scaled to your personal preference as a utility. So yeah, we can definitely do something like that. Please, reach out to our team if that's something you're interested in.
Thank you. Another question on the automated tool. Could you spend or elaborate a little bit more on the automated tool?
So like Rajesh and Brent mentioned, this is an internal tool that we've developed to help you be efficient on PRC 027 to achieve efficiency and quality. So one of the cool things that this tool does is it generates discrepancy reports to help the engineer basically validate the system model against, nameplate information or impedance information from transmission planning, or even just compare the impedances in Aspen to that of the setting files. And the reason this tool is helpful is because, like I said, we do need to get the Aspen model correct and the data right prior to doing the coordination check. The other thing that this tool does is it also generates an impedance report. So this is nothing but all of the impedances within the wide area coordination that we select, and then presents us with the impedances, which is easy for the engineer to then compare the output of the tool with data provided by, again, transmission planning operations, and also any data provided by the interconnecting facilities, right? Like their line impedance parameters or fault current magnitudes. So apart from the data verification that helps with validating the model, it also helps with running wide area coordination studies. So the tool can help customize the results of the coordination study. So let's say there's utility A that prefers a coordination time interval of 0.4 seconds as opposed to 0.3, and there's another utility that likes 0.3 under a normal condition. All those differences can be accounted for in that tool, and we can essentially customize our coordination study based on an entity's relay philosophy guide or current practices to ensure that we are complying with those processes when coming up with our coordination study. And the more important thing, like Brent and Rajesh mentioned, is that this tool does a good job of automating what we think is important, but leaving the relay calculation process to the engineer, because we believe that, to achieve quality and help improve the reliability of the grid, we do as engineers really need to appreciate the art and science of protection and use our knowledge and industry experience to create those settings, but also utilize that to review from a quality perspective prior to implementation of them on the field.
Great, thank you. Another customer question here. When SEL is establishing a baseline, how would you determine any fault current contributions from neighboring utilities? Or could the contribution from the neighboring utility simply be ignored?
So for establishing the fault current baseline, we would really like the system to be accurate, right? Because if you do have an interconnecting facility that actually acts as a source of fault current, then we don't want to ignore its contribution, because that is going to contribute to the fault, and that is required for the development of settings because it does, like we discussed in the presentation, affect the pickups of a 51, for example. So good practice would be to ensure that, in the model verification stage that we work with the interconnect facilities to get that required data and model it to the best possible way that we can in our model prior to doing our coordination study or even developing the protection settings.
Next question. When you do a system-wide coordination study, do you consider communication-aided tripping schemes, or do you assume this is worst case and the comm system is down? Goes on to state some utilities do not include the comm tripping in their short circuit models.
So that's a really good question, and really for a pilot scheme, the zone of protection is the protected line. So it really doesn't coordinate with adjacent protection system functions, and therefore it was excluded as part of the standard. But obviously we do need to check for, pilot scheme coordination, because that plays an important role in achieving reliability of the grid. But those elements are not included as part of the PRC 027 standard.
Well, we're at the top of the hour here, it looks like. We have over 80-some questions, so we're going to have to get back to some of you via email that weren't answered here today. We hope you found today's webinar both helpful and insightful. Again, if your question was not answered here today, we'll receive an answer via email. To learn more about this topic, please visit our SEL website. That's selinc.com. Once again, we would like to thank you for your time and hope you join us for future SEL webinar events. Have a good day. Thank you.